Hello everyone and welcome to ROS2 Jazzy tutorials. In this ROS2 Jazzy tutorial, we explain the basics of the ROS2 control library or ROS2 control framework. The ROS2 control library contains a number of packages for real-time control of robotic systems. And over here you can see a brief demonstration. Here, in this RViz simulation environment, you can see a simple robotic system consisting of two links, the first link, the second link, and the single joint. This single joint over here is rotational joint. It enables the rotation of the second link, represented by this blue prismatic element, with respect to the first link, represented by this red prismatic element. And to demonstrate how ROS2 library is being used, I'm simply over here controlling the position. Namely, in this terminal, I will rotate the joint to the position of 0.5 radians. And if I press enter, the robot will rotate. Since this is a simplified model and simplified simulation, we are not actually modeling or animating the actual motion. We are just modeling, or better to say simulating, the start and end position. So over here I'm going to repeat again, and let's say that we want to go back to the original position to minus 0.5 radians. If I press this command and if I enter, the robot will return to its original position. The ROS2 control library enables us to simplify the integration of hardware such as sensors and actuators and deployment of control algorithms. This library implements a number of standard and useful controllers such as PID for set point tracking, then position controller, velocity controller, trajectory controller, differential drive controller, and similar control algorithms. Here's a brief summary of what is explained in this video tutorial. In this tutorial, we explain, number one, how to implement a minimal example and a ROS2 package that demonstrate how to use the main functionality of ROS2 control library from scratch. Number two, how to properly write URDF, Zacro, yaml, and other files that define the ROS2 control parameters. Number three, how to simulate the motion of a robot controlled by using the ROS2 control framework. For simulation, we use RViz. However, in the future video tutorials, we will explain how to use ROS2 control library in Gazebo. In order not to blur the main ideas with too many details, in this tutorial, we are using the simplest possible example of a robot and a simple ROS2 control implementation. The main idea is to teach students how to properly build the package and all the configuration files. Everything explained in this tutorial can easily be generalized to more complex examples and more complex ROS2 controllers. As mentioned previously, in this video tutorial, we explain how to write a complete ROS2 package from scratch that implements a controller that's based on the ROS2 control library. And over here you can see the main content of this package. First of all, we will have this parameters file that defines the robot parameters. Then we will have this model file, which is a Zacro or modified URDF file that implements the robot. Then at the end of this file, we will enter the plugin that defines the controller. Then we will explain how to write this YAML file that defines the robot controller parameters. Then we will explain how to write a launch file that will enable us to run all the nodes with a single Python command, and then we will have to modify the package and CMake list configuration files. The complete package, including all the files, as well as the manual shown over here, that thoroughly explains all the steps that need to be performed in order to build the package and to implement the controller, will be given in the description below. That is, links to these files will be given in the description below this video. Here is the license and the copyright notice. This document, develop code files, lesson video, and all the provided material are referred to as the learning material in the sequel. Number 1. The learning material is the ownership and the original work of Dr. Alexander Haber, who is referred to as the author in the sequel. Number 2. You have the right to use the learning material for personal educational use and strictly for non-commercial use. Number 3. The learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. Number 4. The learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Number 5. Unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Number 6. Unless allowed by the author, the learning material should not be used to organize courses for training engineers working in companies or paid academic researchers. That is, paid students, paid postdocs, paid professors, etc. Number 7. The provided code files and learning material should not be used to train an AI algorithm or a large language model. And number 8. Unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other documents. Okay, so let's start with implementation. First of all, let's talk about prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. So let's verify that you have the proper Linux Ubuntu distribution. First of all, click here and search for terminal. And over here, I'm going to resize the terminal. Okay, to verify that you have the correct Linux Ubuntu version, in the terminal, execute this command. And over here, you should see Ubuntu 24.04. Next, we need to verify that you have the proper ROS2 Jazzy version. To verify that ROS2 Jazzy is installed, in the terminal execute this command. This command will list the content of the standard installation folder of ROS2 Jazzy. And if you see these files, then most likely ROS2 Jazzy is installed on your system. However, let's try to source the environment. That is, let's try to execute this setup.bash file from that folder. And if you don't see an error, this is a good sign. And then finally, let's print the ROS distribution environment variable. And if ROS2 is properly installed, and if you were able to source the environment, as the output, you should see Jazzy. If you see this output, this means that ROS2 Jazzy Jalisco is properly installed on your system. If not, then on the YouTube channel you have several video tutorials explaining how to install ROS2 Jazzy Jalisco from scratch on your computer. Next, we need to install the necessary ROS2 packages and or verify that they are installed. In this tutorial, we will need several ROS2 packages. Some of these packages are the standard part of ROS2 desktop version. However, additional packages will also be necessary. First of all, we need to install Robot State Publisher. This is the standard package that comes together with the ROS2 desktop installation. This package receives the joint state information and by using the robot model calculates the poses of every link and sends the information to the TF topic. The TF topic is used to transmit the transformation to RViz, and RViz is a package that we also need. This package is used to generate a graphics user interface and a simulation of our robot. Then we need the Zacro package in order to parameterize the robot model and create macros. Finally, we need the ROS2 control and ROS2 controller packages that implement the ROS2 control framework. Now, since our understanding is that a lot of viewers of this video are completely new to ROS, we need to mention one very important thing. First of all, let's close the terminal and let's open a new terminal. And let's suppose that in this new terminal, you want to create a ROS2 package, install some additional packages, or to play with ROS2. Before you do that, you need to do several things. First of all, make sure that your system packages are updated and upgraded. To do that, simply execute this command and enter your password. And wait until this command completes. And then press yes, and that's it. After that, you need to source the environment. Sourcing the environment means to execute the setup.bash file. This will configure all the ROS2 parameters. Next, we need to install the packages. Let's start with the robot state publisher. As mentioned previously, most likely this package is already installed on your system. Next, install RViz by executing this command. Then install Zacro package, which is necessary for parameterizing the model. Then install ROS2 control. And finally install the ROS2 controllers. Here, it's very important to learn how to list all the packages. To list all the packages on your system, simply execute this command and you will see the complete list. This list is huge, and sometimes you would like to find a particular package within the list or to verify if the package is installed. For example, let us verify that controller packages are installed. To do that, we will repeat this command, ROS2 package list. However, we are going to use this vertical bar and then grep, which will be used to filter the result, and we are going to display all the packages that contain the word control in their name. And if you press enter, you can see all the packages on your system that contain the word control. We can see control messages, control toolbox, controller interface, and you can see everything. Here's ROS control. This is what we need, as well as additional packages that come as dependencies of ROS2 control. Okay, the next step is to create the package, URDF, Zacro, yaml, and launch files. So let's learn how to do that. Here, to engrave in your mind that every time you want to play with ROS2 in the terminal, you need to source the environment. Here I close the original terminal and I'm going to open a new terminal. And then, since I want to create a package, I need to source the base environment. To do that, I need to execute this command. And don't forget to do this. Then let's make sure that we go to the home folder, and in the home folder let's create two folders. Let's create the control_ws. This is our workspace folder, and inside of that folder let's create the source folder. Then let's navigate to the source folder, and inside of this folder we are going to create an empty package. To create the empty package, we need to execute this command. And let's explain what we are doing. We are executing the command called ROS2 package create. Then we are specifying the build type. I want to use the CMake build type. And finally, I'm giving the name to the package. The name of the package will be demo control. Press enter. And remember, every time you want to create a new package, you need to go to the source folder. Keep in mind that thing. Okay, now if you type this command, you will see a new folder. Navigate to that folder, and inside of the folder you will see two new folders and two files. Let's briefly explain what are these files and folders. First of all, CMake lists and package.xml are configuration files. These are the configuration files that will contain additional parameters necessary to build, or better to say, to compile our package. Then we have the include folder and we have the source folder. The include folder can contain, for example, some header files or something similar that needs to be included, and the source folder can contain Python and C++ implementation of our package. In this video tutorial, we are not going to create Python source and C++ files except for the Python launch file, and consequently we are not going to use the source folder. Instead, we are going to create 3 additional folders. Here they are. The first folder is launch, the second folder is model, and the third folder is config. So let's execute this command, and then let's list the content. So let's start with the config folder. The config folder will contain 2 files. It will contain the RViz configuration file as well as the controller YAML configuration file. Then the launch folder will contain the Python launch file, which will configure and start all the nodes, and then the model folder will contain the model implementation. In our case, the model will contain 2 files. The first file will be the file with parameters, and the second file will be the actual robot URDF or Zacro file. Okay, so let's start. First of all, let's navigate to the model folder. Here, to create the files, I'm going to use the Visual Studio Code. However, you can use any other editor. To start Visual Studio Code, I need to execute this command. If you don't have Visual Studio Code on your system, then you can use one of our tutorials. You can simply go to the YouTube channel and search Visual Studio Code install Linux Ubuntu, and you can watch that video tutorial if you want to install Visual Studio Code. Okay, so let's create the first parameter file. To do that, click on File, New File, and call the file as parameters.zacro. Zacro or Shacro or Xacro is the extension, and the name of the file is parameters. So press Enter and save this file in the model folder. It should be, keep in mind, parameters.zacro. And here's the file. Here, to save the time, I'm simply going to paste the content of the file, and I will explain it. First of all, let's explain the purpose of this file. The main purpose of this file is to define the model parameters. Namely, here we are following a very disciplined approach of implementing the robot geometry. We are going to parameterize the complete geometry, and then we are going to also parameterize the moments of inertia, mass, etc. So how to do that? Well, let's go back and let's look over here. Here's the link. Its dimensions are A, B, and C. These are the dimensions in the x-axis, y-axis, and the z-axis directions. Then we have this center of the link, which is denoted by the S, and then Q is the distance from the base to the center or the origin of the first joint. Namely, the robot will consist of 2 links. Both links will have the same dimensions, which are parameterized by A, B, and C. Then the first joint is located over here, and it's a revolute joint, and everything is parameterized. So going back to this file, let's explain what is written over here. Here we are specifying that this is an XML file. Then over here, we are inserting a comment. We are explaining what this file is about. Then this is the standard line. You need to start this file with robot tag, and you need to end the file with the robot tag. So keep in mind that thing. Then here again is a comment, and here we defined the dimensions A, B, and C. And note over here that we are defining them by using parameters. Namely, A, B, and C are parameters, and Zacro property means that later on, when we use, for example, A, B, and C, instead of that symbol A, B, or C, the corresponding values will be given. Okay, here you can see that the links are prismatic, and A dimension is 0.1. Let's bring up this graph. A is 0.1, B is 0.1, and C is 0.8. Okay, then we need to define the center of the mass location and center of the link with respect to the link frame. The name of the variable is S, and the value is C over T. 2, actually the height divided by 2, and that's precisely the location of this point with respect to the base, and the symbol is S. Good. Then we need to define the symbol for Q. Here is a Q, and the value is the height of the first link minus C over 4. And in that way, we define this point over here, and its location is Z direction with respect to base. Good. Then we need to define the material density. Here I'm assuming aluminum. Then we need to compute the mass. The mass is simply denoted by M, and its value is density multiplying the volume. Then we need to define links moments of inertia. Since this is a prismatic element, the formulas for the moment of inertia are given over here. Ix, Iy, and Iz moments of inertia. Here are the parameters, and we simply implement these formulas over here. Then we define a macro that defines the complete inertial section of our element. Namely, we need to define inertia matrix or tensor of inertia. First of all, we need to define the displacement and orientation of the center of the mass frame of the link with respect to base. Namely, we need to say that the center of the link and the corresponding coordinate frame is located at this point over here. Consequently, over here we are specifying the XYZ translation to be 0, 0, and S, and we don't have any rotation of the coordinate system with respect to the link coordinate frame. Then we need to specify the mass, and then we need to specify the inertia. We simply use the previously defined parameter for Ix, Iy, and Iz, and we set the other moments of inertia 0 since our element is symmetric with respect to its center frame. And that's it. And this is our inertia. And then later on in another file, we are going to use this macro to simplify everything. Then we need to specify the colors. Here I'm defining the blue color and defining the red color, and note that these RGBA are actually codes. R stands for red, G stands for green, B stands for blue, and A is the transparency. For example, here 001, 1 means that blue is 1 and transparency is 1. This means that the element is completely non-transparent, and that's it. Okay, so let's save this file and let's continue. Next, we need to define the Zacro file or the URDF file that will use these parameters and that will define the robot model. To do that, click on File, New File, and call the file as model.zacro and press Enter. And save this file inside of this folder, and let's paste the content of this file and let's explain everything line by line. Okay. First of all, this line is the standard line. This tells to the ROS system that this is the XML file or the URDF file implementing the robot model. Then we need to start the robot tag, and at the end of the file, we need to end the robot tag. Then we need to specify the name of the robot. I'm calling the robot a simple robot, and this line is standard. Over here, we need to include the parameters.zacro file, and we do it like this. We use this tag zacro include, and we specify the file name. First of all, here we are trying to find the absolute path to our package folder. Namely, if you go back to the terminal, this is the absolute path to the package folder, and this find demo control will actually bring this path or write this path or substitute this section with the actual path. Then the file is located in the model folder, and the name of the file is parameter.zacro. Now this file defining all the parameters is included. Here we need to define links and joints. We start with the world link or the fixed joint. First of all, whenever you model a robot, you need to fix the world frame or the world coordinate system. Here I'm defining a fictitious link called world, and I'm defining the joint name, which is fixed joint. Its type is fixed, its parent link is the world link, and the child link is the first link, and that's precisely this link over here. Namely, the first link is simply called the first underscore link, and the second link is called second underscore link. This is very important. And in this way, we have defined the world coordinate system, and we can refer to this world coordinate frame later on. Next, let's define the first link of the robot. We start the link tag, we end the link tag, we define the visual representation. It's a box with the dimensions A, B, and C. Then we define the displacement orientation of the geometric center of the link with respect to the world frame. Here what will happen, I will simply shift or translate this link such that its center is located at the point S, and the translation is actually given over here, and I'm specifying the name of the color of the element. It's red. Note over here that this red color is actually defined over here in the parameters file. Good. Then we need to define the collision block. The collision block is simple copy of the visual block, and that's it. And finally, we need to define the inertia of our element. Over here, it's basically inertia is simply the inertia defined over here. So we simply use this macro and we just type inertia, and magic happens. Instead of this section over here, this complete section will be filled in with the appropriate values. And that was our first link. Next, we need to define the second link of the robot, and we need to define the first joint. First of all, we need to specify the joint name. The joint name is first underscore joint. The type of the joint is a revolute, or it's a simple rotational joint. Then we need to specify the parent link, which is the first link, and we need to specify the child link, which is the second link. Again, the first link is this link, and the child link is this link. Then we need to specify the origin of our joint. The origin is at location, or better to say translation 0, B, and Q from the previous link frame. Namely, these coordinates over here are the coordinates of this point with respect to the link frame located over here. And that's it. Simple as that. Nothing special. We don't have rotation. Then we need to specify the rotational axis. Our link will rotate around the y-axis, and consequently over here we need to specify 0, 1, 0 as rotation. Next we need to define the limit for the torque. It's 5,000. Limit for velocity 10 radians per second, and a lower and upper rotational limits. Then we need to define the damping, and we need to define the friction, and that's joint. Next we need to define the second link. The second link definition is almost the same as the first link, and it's actually the same definition. We have the visual representation, we have the collision, and we have inertia, and that's it. In this way we have defined all three links. Next, we need to proceed with ROS2 control plugins and definition. Now, in this video tutorial, we are not going to go too deep and explain the theory behind the ROS2 control library. You can simply go to the ROS2 control library website, and then you can read more if you're interested to know about theory. We are going to talk about implementation, and later on we are going to explain in more details what are the topics, how this library works. That is, this will be done through almost at the end of this video tutorial. Now, whenever you want to use any section or any package from the ROS2 control library, you need to basically define this tag over here, or you need to define the type of control plugin you want to use. You start with the ROS2 control, and then you specify the name. The name is robot controller, and the type is system. Now, over here, you can simply skip this part since it's being commented. I will explain the purpose of this once I explain everything else. And over here, you need to define the hardware tag, or inside the hardware tag, you need to define your plugin. Here, for illustration purposes, I'm going to use a simple plugin called mock components generic system. This is the simplest possible plugin, and I suggest to everyone to start with this plugin, since this plugin ignores a bunch of things and simplifies everything. It will simply mirror the control commands into the joint state variables, and the link will move automatically and immediately. And that's precisely what you have seen at the beginning of this video tutorial. Now, here you need to define several parameters, calculate dynamics. Here I'm using the standard values. Then you need to define the custom interface with following offset. Here I will leave it empty. Disable command false. Mock GPI commands false. Mock sensor command false. And position state following offset, it's 0. These are the standard parameters, and you can find their detailed explanation on the website. Okay, however, this will work, and this is a minimal configuration. Okay, then you need to define the joints. So what are the joints that need to be controlled? This is very, very important. Here we are controlling the first joint, and here you're referring to previously defined joint. So if you go back over here, you can see how the joint is being defined. It's a revolute joint, and we are precisely defining control parameters for that joint. We are specifying command interface that it is position. Then we need to specify the parameters for position, minimum and maximum values, and that's it. So that's our command interface. So we are going to control position. You will see later on here the min and max values, and that's it. And then you need to define the state interface name. It is position. So what is the state? The state is actually the angle of your rotation. Here we are using the word position. However, a more precise name would be angle. However, let's leave it as it is. And then we end the joint tag, and we end the ROS control, and that's it. This is very, very important definition. So to summarize, whenever you want to use ROS control, you will have this URDF definition that explains the parameters of your controller. You need to define the plugin that you're going to use, and then you need to the plugin is over here, and you need to define the joint that you're controlling, and you need to refer actually to the joint from the previous URDF description, and you need to define these parameters. If you have, for example, 10 joints, you will have here 10 different sections for the first joint, second joint, until the 10th joint. Now, let's go back and let's explain what's happening over here. You can see that I commented this tag over here, and you don't need to write it down in your implementation. However, here I'm demonstrating how to use another plugin. This is a plugin from one of the demo examples that you can find online. And here are some parameters that are necessary to use that example. Here I'm just doing this for illustration purposes. For example, if you want to use ROS2 Gazebo interface or plugin, then you will specify it over here. Similarly, you can use differential drive, robot, or any other controller, and you will need to specify the plugin over here. That is, you always need to go or to start with a plugin. Now, note over here that we didn't specify the type of the controller that we want to use. We can use feed-forward controller, feedback controllers, PID controllers, differential drive controllers, etc. You actually define the controllers that you plan to use in another file. And over here, I will bring up the file and show you how it looks. So here it is. And let's copy its content. The name of the file should be robot_controller.yaml. So let's create that file. Go here, click over here, new file, and call the file robot_, or let me just go back and verify the name once more. It should be robot_controller. So let's do that. File, new file, robot_controller.yaml. Now make sure that you save this file inside of the config folder. That is not inside of the model folder, but instead in the config folder. And the file is robot_controller.yaml. And here it is. And here I'm going to paste the content of the file. And let's explain the purpose of this file and the sections. This is the YAML configuration file. It has two sections. It has the control manager section, and it has a section dedicated to the controller that you plan to use. So control manager needs to contain some ROS parameters. First of all, you need the frequency of control. In this case, it's going to be 10 Hertz. That is 10 times per second we plan to send control signals. Then over here, you need to define a joint state broadcaster, which will help us to broadcast the joint state. And then here you need to specify the type of the controller that you plan to use. In this particular case, I'm using the feed-forward controller. It's a feed-forward position controller that will control the position or the angle of rotation of the robot, and over here you need to specify the type. Then, after you do that, you need to specify again additional parameters for the use controller. Forward position controller, you need to specify the ROS parameters, and here comes the main part. You are now saying here that you want to control the first joint, and the first joint is actually defined in your model.zacro file. It's defined over here, and in addition to this definition, over here you have several additional plugins, and you have here this section which gives more information about this type of joint and how it's being interfaced and controlled. Okay, and then interface name is position. That's it, simple as that. Make sure that you save this file, and let's continue further. The next step is to create a launch file, and here it is. The name of this file should be display.launch.py. So let's create that file. Click on File, New File, and call it display.launch.py. And save this file inside of the launch folder and create the file. Let's now go back here and let's paste the content of this file, and let's explain the purpose of this file. The main purpose of this file is to start several nodes and to configure them with a single Python command. Namely, once we implement everything, we are going to run everything by simply running this Python file. The purpose of the file is to configure and to bring up the nodes. And let's see what we need to do inside. First of all, we need to import the necessary library. Then we need to specify the package name. Our package name is demo_control, and it's very important that this name matches the name of this folder. That is the base folder of the package. Next, we need to define relative paths of several files with respect to the package path. First of all, our model.zacro is in the model folder. That is, it is inside of this folder, and you're specifying the relative path with respect to the package folder, which is demo control. You do the same thing for the RViz configuration file. The RViz configuration file will be placed in the config folder. So where is the config folder? It is over here. Note over here that config.rviz still doesn't exist. However, we will create it in the future. That is at the end of this tutorial, once we bring up the first simulation. And then we need to specify the relative path with respect to the robot_controller file. That's precisely this file over here. So let's make sure that we save everything, all the files. And let us now write a function that will configure and start the nodes. First of all, you need to retrieve the absolute path to the package. So this is not the absolute model path, this is the absolute package path. Okay, this is very important. So the package path is defined like this, or retrieved like this. You call this function, then you specify the package is equal to package name, and this is the package name, and then you're simply calling find package name, and this will return the path to this particular folder, the absolute path. Then you simply need to create several absolute paths to the model and to the configuration files. You get the absolute model path to our model.zacro file. Here you are creating the absolute path to the RViz configuration file by simply joining the package path with the RViz relative path, and you do the same thing for the Zacro model path, and then you do the same thing for the robot controller YML file, you're retrieving its absolute path. Here for verification, I'm printing the Zacro model path. You can simply omit this step. I'm doing this for debugging purpose. And then over here, I'm getting the robot description for the Zacro model file. I'm simply calling Zacro, I'm calling process file, and then I'm passing the path to the Zacro model file. That is the path to the model.zacro, and I'm converting everything to XML. Now behind the scene, what will happen, these macros will be called, they will convert everything and insert numerical values, then the numerical values will be inserted inside of this file over here. And then over here, I need to define a dictionary with the robot Zacro description. I'm simply calling it as robot underscore description. And then here I'm defining and configuring the nodes. I will need several nodes. First of all, I will need the robot state publisher node. And consequently, over here, I'm explaining how this node should be started. I'm specifying the name of the package, I'm specifying the name of executable, where it should be executed. It should be executed both to inside of RViz and inside in the background, and I'm specifying the parameters. Then I'm explaining how RViz node should be started and configured. The package is RViz, the executable is RViz, name is RViz, where I want RViz to be displayed on the screen, and then what do I provide as arguments? I provide the path, or better to say the absolute path, to this configuration file, which will be created later on. And now we have these three additional sections that will help us to use the ROS2 control library. First of all, we need the ROS2 control node. The package, watch out, here is control manager. The executable is ROS2 control node, and here we are passing as parameters ROS2 control path. So what is this ROS2 control path? ROS2 control path is defined over here. It is actually the absolute path to this robot underscore controller YML file, and that's it. Then we need a joint state broadcaster spawner. Namely, we will have to broadcast the states. And for that purpose, we need to call, or better to say, to specify the controller manager, executable is spawner, and argument is joint state broadcaster. Then we need our controller spawner, we need a forward position controller. So again, control manager spawner, and then we are specifying over here forward position controller, and then we are specifying the parameter file. That's precisely the file that's also being passed to ROS2 control node. And that's it. And finally, we combine everything and return. We define these additional parameters for using graphics user interface, and then we specify what we are starting. We are starting the robot state publisher node, the RViz node, the control node, joint state broadcaster spawner, and the robot controller spawner. And that's it. Make sure that display.launch file is saved in the appropriate folder. It should be saved in the launch folder. And that's it. Next, we need to modify two additional files. These are the configuration files. So click on File, Open File, go back to the package folder and open package.xml. And over here, below these test dependencies, you need to enter additional dependencies. That is, you need to tell to the ROS2 system and to the package manager that your package depends on some standard ROS packages. And these standard ROS packages are, let's see, control manager. Why I'm using control manager? Well, because over here, I'm using control manager. Simple as that. Why I'm using forward command controller? Because I'm using here forward controller, right? Inside of this file, we are using forward controller. Then we have the robot state publisher. Since in this file, I'm using the robot state publisher node. Then we have the Zacro, since I'm using Zacro macros to simplify the parameterization, and I'm using RViz. Simple as that. Next, we need to edit and modify the CMake file. So open the file and open the CMake file. And over here, we need to tell to ROS2 build system that we have created files in additional folders. Namely, if you remember, we have created the config folder, the launch folder, and the model folder. And we need to tell to the build system that these new folders are being created and that there are files inside of this folder, and we can simply do it like this. Let me copy this and let's not make an error. And here it is. So what we are installing? We are installing the directory called launch, directory called model, and the directory config, and here we specify destination, and that's it. And let's save this file. And that's basically it. These are the files that need to be modified or created. The next step is to build a project. For that purpose, make sure that you go to the base workspace folder, and inside of this folder, let's install the ROS2 or Python ROS2 such that we can verify that everything is installed nicely, that is, that all the dependencies are installed nicely. Then let's initialize and update ROS2. Here, if you see some error, you can simply ignore, and then let's update. And then finally, let's run this command to make sure that everything is nicely installed. And then as the output, you should get this message, all required ROS2s installed successfully. Next, let's build our package. To build our package, make sure that you're in the base folder. And then over here in the base folder, you need to call colcon build. You want to do symlink install, packages, select, and the name of the package is simply demo control. Press enter, and let's hope that there are no errors. Beautiful, no errors. Okay. The next step is to open a new terminal to source now not the base environment. Instead of the base environment, you need to source or execute setup.bash file from the created package and press enter. And then let's run our display.launch file. You simply run ROS2 launch, name of the package, and name of the display.launch.py file, and that's precisely this Python file, actually this Python file. Make sure it's being saved and then run it. And here let's go over and let's search for an error. Okay, let's see if you see something red. Let's see. Okay, nothing red, nothing, no errors, no errors, no errors, no errors, no errors. Maybe some warning. I currently don't see warning. Okay, good. So no errors. However, if you go to RViz, nothing is displayed over here. Well, that's perfect and that's normal. And actually, I wanted to say that's perfectly normal. Why is that? Well, in order to display a robot model, RViz needs its own configuration file. To enable that configuration file, click on Add, or better to say to first configure and then to create the configuration file, click on Add and click on Robot Model. And here it is. Now expand the robot model, and then over here as a description topic, enter robot description. Aha, link appeared. However, the link is not properly positioned and the colors are not properly displayed. To display them properly, click on fixed frame and make sure the world frame is selected, or better to say that the fixed frame is the world frame, and here it is. Beautiful. This is our model. The next step is to save this configuration such that the next time we run everything, we don't need to do these adjustments. To do that, go back to the display.launch file and see where should be the configuration file. Here it is. Here's the name of the configuration file. Let's copy this name. Let's click on File, save config as, then go to the base folder. This is your workspace folder. Go to Source, go to the Package folder, and then go to the Config folder, and over here paste the name. Click on Save, and now the configuration is saved. Next, go back to the terminal, press Ctrl+C to kill RViz, go back to the original terminal, repeat the build command, then go back to this terminal, to the RViz terminal, source everything again since we build everything, and then let's repeat ROS launch command, and here it is. Magic happens. Now make sure that this window is active, and let's continue further. The next step is to learn how to use the ROS2 control library. To do that, open a new terminal while the previous two terminals are active. source the base environment. That is, source the base ROS2 Jazzy environment. And then let's list all the hardware interface of our ROS2 control. To do that, you need to execute this command, and voila, beautiful. Let's see what are the command interfaces. The command interface is first joint position. You can see it's available and claimed. This means that it's perfect. It's available and we can use it. And the state interface is first joint position. Beautiful, beautiful. Okay, now if you go back to the YML file, you'll see its first position and the interface name has actually the joint is first joint and the interface name is position. And consequently over here you see first joint position. If you now see the joint state broadcaster over here, this state interface comes from the joint state broadcaster, but this is not very important at this moment. Okay, next let's see additional information. So let's list all the controllers and see if the system can recognize our controller. Here it is. We have the forward command controller, it's active, and we have the joint state broadcaster, Perfect. Next, let's analyze all the topics. So let's see what are the topics we have. And let's see what do we have. Click point control manager, perfect. So you see a bunch of topics that are related to ROS2 control. Then you can see for the forward position controller, and you can see one very, very interesting topic. It's forward position controller commands. And through this topic, we are going to send the control messages. So how to send the control messages? There are two ways to do it. To control the robot joint position, we need to enter this command. Namely, we need to call ROS2 topic pub. Pub or pub stands for publisher. Then we need to specify the name of the topic. And then we need to specify the type of the command we are sending. We are sending a standard message float 64 multi-array. And then we need to specify data, and over here inside of these square brackets we need to specify angle in radians. This is the desired position of the robot joint or desired angle of rotation in radians. And note that this is the position, not the relative rotation. Now, over here there is a new line. However, when you enter the command, you shouldn't enter a new line, otherwise you will have an issue. So let's enter this command. Go back in the terminal in which you source the base environment, and then bring up the RViz. Here is the RViz. I'm going to change the size of the RViz window such that you can see the position control. Then let me now go like this. First of all, I'm going to bring back the robot to 0 position. So I can enter this, and after we evaluate the command, you can see that the joint has moved, and this is the neutral position. Okay, so let's rotate the robot for a certain angle. I need to press Ctrl C over here, and then let's change the angle over here to, for example, 0.7 radians, and press enter, and you'll see the rotated joint. And here it is. And in this way, you can control the robot angle of rotation. So let's go back to minus 0.7. Let's see what will happen. You're going minus 0.7. Then let's test the limits. The limits are actually pi over 2. It's, I think, 571. Let's go to this limit of rotation. Yes, here is the limit of rotation. And let's go back to the positive limit of rotation. If you do this, you will go to the positive limit. And that's basically it. As a final step, we need to learn how to visualize the robot graph. That is, how to visualize the nodes, as well as how to echo the states. Namely, let's go back and let's go to the terminal, open a new terminal, source the base environment in this terminal, and then let's see what are the states of our joint. For that purpose, you need to evaluate this command. and you will see in real time the update of the joint state, and you can see the angle of rotation over here. Okay, now that we know how to do that, let's visualize the node graph. To do that, we need to execute this command. This command will actually install RQT graph, and then make sure that you're in the window in which the environment is being sourced, and simply run RQT graph, and you should see something like this. And let's analyze what's shown over here. The joint state broadcaster is transmitting the message to joint state. Joint state is submitting the further message about the joint state to robot state publisher. Robot state's publisher uses the URDF and creates or basically solves the forward kinematics problem and sends the coordinate transforms to this topic over here, and then from here RViz can display the position. So this is a feedback loop, or better to say, this is the loop used to visualize the RViz, the motion of the robot in RViz. Okay, that's all for today, and thanks for watching.